Hi, and welcome back. This is lecture 2 of 2 on chapter 8 material. Now, as we saw from the previous lecture, chapter 8 covers concepts like conservation of energy and potential energy. Now, what I'd like to start off today talking about is what happens when your problem doesn't have energy that is conserved. Now, the terminology that's generally used is like this. We refer to the problem or whatever situation that you're talking about as the system. So either your system internally conserves energy. That means the energy isn't allowed to get out or to come in to your problem or whatever it is you're looking at from the outside, or it does. If it's not allowed to come out, then things are conserved. If energy is allowed to come in from the outside or escape to the outside, we say it's not conserved. Now, one question you might have is that okay? So all the stuff that we've dealt with up to this point, for the most part, deals with situations that allow us to use conservation of energy. Can you still use arguments that surround energy to deal with situations in which it's not conserved? And the answer is absolutely yes. It's a little more complicated, but you can. So that said, if you think about what energy conservation means, it means that your initial energy and your final energy, when you add them all up, they're equal to each other. So we know that you can take and you can move the term here on the left-hand side to the right-hand side. And if you do that and you sort of switch places, then what that means is that the change in energy overall is zero. This would be conserved. Now, a lot of times, though, what happens is that the initial energy and the final energy aren't equal to each other. And that's because there's something going on inside the problem that allows the energy in question that's lost to be lost to the outside. Now, to use an example that's not necessarily classical, if you think about, for example, a balloon that contains hot air. Now, if we think of our system as just being the balloon and the air on the inside, then this is a situation in which energy is not conserved. Because what happens is that the balloon is allowed to expand. We know when you heat things up, they expand. So if your balloon expands, then it can, as it expands, if you think of it now being this big, we'll say, it has exerted force potentially through contact with the surface area on the environment, which means that work has been done. And energy actually will leave to go to the outside. And, if you look at the initial and the final energy, they aren't equal to each other. So this is clearly a situation which is not conserved. Okay, so we're going to stick with definitions that look like this when it comes to situations in which energy isn't conserved. Although on the right-hand side, you may not see W, you may see, sometimes you see Q. Q would be just sort of a generic energy in or energy out. It could be positive, it could be negative. You never know. But like I said, in this class, we're going to be dealing with this format right here. So that said, let's work an example in which we can use energy arguments to solve our problem, but energy is not conserved. This one right here. So in this problem, we have a block that has a mass of 5.25 kilograms, and it sits 2 meters up an inclined plane that's raised to 15 degrees. Now, if the block is released from rest and the coefficient of kinetic friction between the block and the plane is 0.15, what I want to know is what the speed of the block is when it reaches the bottom. Now, we have actually worked problems similar to this when we were doing kinematics, okay, when we're looking at forces and stuff. And you can still work that problem this way. And in fact, it might be easier to work it using kinematics and not with energy. Okay, so that said, let's just take a look. We'll label some stuff on our problem here. So here is our distance up the incline, right here. Oops, what I'm doing there is use a line like that. So this right here would be 2 meters. Okay. Our angle here we know is 15 degrees. Okay. There is a coefficient of kinetic friction of 0.15. And we know the mass of our block here is 5.25 kilograms. Okay. Now, so let's just talk about the energy at the beginning of the problem, at the end of the problem. Now, what's going to make this thing slide down the incline is gravity. So we know we're dealing with a potential energy here that's going to have a form that looks something like mgh, or, as I said, mg, times the absolute value of y, or delta y. Now, so we know we're dealing with that potential energy. Okay. We also know that this thing is moving, so there's going to be a kinetic energy that we have to deal with, and the form of that's going to look like 1/2 mv squared, right? On the other hand, if you look at the other forces that are present, and let's just go ahead and draw them. We have a normal force, we have gravity, and as this thing slides down, there's going to be a kinetic frictional force that goes that way. Okay. Now, so what's going to happen is as this thing slides down, it's this force right here, this kinetic frictional force, that's going to be taking energy out of the system. Now, where's that energy going? Well, if you take your hand and you rub it really quickly while it's pressed down on the table, you feel it get warm. So you'll also hear noise. So that energy is being lost to sound, it's being lost to heat as well. And in general, you can't really recover it, or at least not 100% of it. So that said, we know how to work problems like this. Like I said, if we use kinematics, and the way to do this is to start off with a force diagram. So let's do our force diagram. And I'm going to work in the frame that we typically work when we are working when we're dealing with an inclined plane problem like this. We rotate it. So what we're going to do is we're going to rotate this thing at least just to examine the forces such that our problem looks a little bit like this. So this would be our block, like that. And it would be moving this way as it slides down. And we're going to call this, again, the positive x direction. Now, so here's our block in the center. We're working in this coordinate system now. That means we have a normal force that goes up. That means that we have, gravity, which is going to point down this way somewhere. And then we have this kinetic frictional force, which goes off like that. Okay. So we'll label these F sub k. Again, here's your normal force. And then, here's gravity. And, we know this is theta. And if you were to sum up the forces, and we're just going to go ahead and do that, be formal about it, you have your kinetic frictional force, you have your normal force, and you have your static frictional force. And that's equal to m times a vector. Okay? So in the y direction, which would be, this, okay, in the y direction, you have a normal force pointing up, and then you have the y part of gravity pointing down, and those are going to balance each other out. Okay. Now in the x direction, you have the static frictional force part, or not the static, rather. What am I doing? Looked at that and I saw s. That should be a g. All right. So you have the x part of gravity here, and opposing it, you have the kinetic frictional force. And these are going to act to cause that mass to experience acceleration along the x direction. Now, the reason why I'm doing this force diagram is because I'm going to use it to help me figure out what this static or what this kinetic frictional force feels like. When I figure out that form, I can talk about work. Okay, so here, what I'm really looking for, looking at the forces here, is what F sub k looks like. Now we know F sub k is going to have the form of mu sub k times the normal force. So we need to get the normal force from this, and it's coming from this part right here. Okay, So let's just go ahead and take our gravitational force here and break it up into components. So there's the y part, there's the x part right there. Here's our angle theta. And I'm not going to bother even looking at the x stuff. I just want to look at the y stuff. And the y part of gravity here is going to be a cosine. So what I see here is that FGY is going to equal to FG times cosine of theta. And if I rewrite that, that's mg cosine of theta. Now, so I'm going to plug this in here to this, and because that tells me what the normal force is, right? It tells me it's that. So what that means is that my frictional force here looks like mu sub k mg cosine of theta. Okay, so this is the force that's going to be doing work, taking energy out of the system. Okay, so let's just sort of table this. I'm going to box it over here just to keep track of it. And we're going to table this for a moment. And now let's talk about, again, the energy stuff. So when our problem begins, our block is sitting up the incline this high right here. So this is how high up the incline, or rather how high above the ground, let me rephrase that, my block sits. Now the reason why I'm interested in knowing that is because my potential energy depends upon how high above the ground I am. Now we're not given that, but we're given how far up the incline this thing is. So we can easily figure out what this height is. This height, if you think about it, is going to be 2 meters up times sine of theta. Now, I don't like writing numbers and stuff inside these things. So let me just write givens out. And that way I can work with variables as opposed to numbers in my equations. So the height this thing is above the incline, okay, h, is going to come from how far up this thing is. And I'm going to call this d, okay? So d here is 2.00 meters, which means that the height above the ground this thing sits is going to be d times sine of theta. Okay, now let's go ahead and write everything else in here. Let's see, my mass is 5.25 kilograms. Let's see, theta is 15 degrees. The coefficient of kinetic friction is 0.15. My initial velocity, because this thing starts from rest, is 0. Okay. And I'm trying to find how fast this thing is traveling at when it gets to the bottom. So I want to find v down here. Okay. Now, so up at the top, if I think about energy, okay, I would have kinetic energy plus potential energy, but it's not moving. So it starts off at rest. Initial kinetic energy is 0. So it's all potential energy, which would be mgh, or as we noted before, h is d sine theta. So mg times d sine of theta. Okay. Now at the bottom here, this thing doesn't have the potential to slide past the ground at the bottom. Okay, so it can't continue to fall if you want to think of it like that. So even though, my total energy is kinetic energy plus potential energy, the potential energy at the bottom is 0, which means it's 1/2 mv squared. Now this is what I'm trying to find here is this v. Okay, so the deal here though is we can't just set these things equal to each other because we have energy being lost as a consequence of the kinetic friction. Okay, so what we are going to do though is note the fact that whatever change in kinetic energy we have, whatever change in potential or whatever change of the total energy we have rather, is going to be E minus E naught. And that's going to be a consequence of the work that's being done by this frictional force. Okay, so here's the deal. If you think about it, this right here would be the direction of dr. Okay, but this right here is the direction of the force. So if you think about the work that would be done by that force as this thing slides down the incline, first of all, the force itself is constant, which means that we can write it as, F dot delta R. Okay, but look, dr or delta R here is literally down the incline, which we're calling x, uh, delta x hat. Okay, F sub k is up the incline. Okay, it's let's see, where did I put it? In the box right here. Mu sub k mg cosine theta. Along the minus x hat direction. Okay, so when I do the dot product, I'm going to get a negative, and at the end of the day, it's going to look like mu sub k mg cosine of theta times delta x with a minus sign out in front because it's negative. Okay, so what that means here is the change in kinetic energy. If you think about it, change in kinetic energy. There I go again, right? The change in the total energy, rather. That's what I get for doing the work energy theorem, right? The change in the total energy is going to be negative. That means that my final total energy is less than my initial total energy because energy is being lost in the form of heat and sound as this thing slides down the incline. And it's being lost to the tune of mu sub k mg cosine of theta times delta x, or d. That's what delta x is. That's how far down the incline we go. Now, so what's delta E? Well, that's your final energy minus your initial energy. Your final energy, looking at this stuff right here, is 1/2 mv squared. Your initial energy is mg d times sine of theta. And this is equal to minus mu sub k mg cosine of theta times d. Now, the first thing you see is the masses cancel. Okay, so it doesn't matter what is being slid down the incline. The only thing that matters is what the coefficient of kinetic friction is. Okay, so I have 1/2 v squared. I'm going to go ahead and move this over to the right-hand side. When I do that, I get g times d sine of theta minus mu sub k g cosine of theta times d. Okay, and if you look, there's a lot of stuff in common here. There's a g, there's a d. What's left is sine of theta minus mu sub k times cosine of theta. Multiply both sides through by 2, and then take the square root. Define v is going to be the square root of 2gd sine of theta minus mu sub k cosine of theta. So if I plug stuff in here, 2 times 9.8 meters per second squared times 2.00 meters times sine of 15 degrees minus mu sub k, which is 0.15, times cosine of 15 degrees. Now, I found my calculator. It's in our playroom. And I get 2 times 9.8 times 2 times sine of 15 minus 0.15 times cosine of 15. Let's see here. 2.11 meters per second. Okay, so looking at sig figs, I have 3 here, I have 3 here, I have 2 here, I have 2 here. So this is going to be something like 2.1 meters per second. Now, so this is what you would get, if you if you use the energy approach to solve the problem. Now, if there was no friction present, then that means that, and we'll just take a look at the difference between the two. If there was no friction present, that means that E would equal to E naught, which means that we would be solving 1/2, 1/2 mv squared is equal to m times g times d sine of theta. Now, we can solve that real quick just to sort of see the difference between the two. In that case, your v would equal to 2 times g times d sine of theta. And if you just plug the numbers in, you're going to get 3.2. So you can see there's a substantial difference between the speeds, right? And that's all due to the fact that energy is being taken out of the system. Now, this wasn't bad. This is not a bad approach. There wasn't a whole lot of work, at least in my opinion, to get from, the beginning to the end. But you may find it easier to take and use, forces and kinematics in order to find the equations of motion and just, solve for v at the bottom. It might be easier. And if you remember, when I was talking about conservation of energy in the last video, one of the things I pointed out is, you have that sort of saying that, if your only tool is a hammer, then everything looks like a nail. People get, so mired into the idea of conservation of energy because it's so easy. Okay. But it may be that, in this particular situation, for example, that solving this using kinematics would be the easiest thing. And if you take a look over here, for example, we have the acceleration. Okay. And at the end of the day, it's going to be constant, which means that all we would need to do would be to find A and then just write out our kinematic equations and ask the question, what is V when it gets to the bottom? So in truth, it probably would be easier to use that in this problem. But this does a good job illustrating the fact that you can use energy approaches in situations like this. Now, that said, the next topic I would like to talk about is going to use a spring as an example. And this deals with getting equations of motion from energy. So energy is all nice and well, but we know that one of the things that energy is lacking is time, and it's also lacking a sense of direction. There's no, remember, energy is a scalar quantity, it's not a vector quantity. So if you think about conservation of energy, specifically how energy is a combination of kinetic energy and potential energy. So let's just think about conservative situations. So this only really works for what's going on with me today? Where energy is conserved. There is a way you can get the equations of motion. Okay. Using energy. There is also a way that you could solve for times and things like that. And that is to take this right here and note the fact that E on the left-hand side is constant, just a number. And U, the potential energy in a conservative situation, only depends upon coordinates, X, Y, and Z. So in this situation right here, this is a 1D situation. And I'd like to consider 1D for the sake of convenience, because when you move beyond 1D, it gets more complicated. All right. So first of all, we know K looks like 1/2 mv squared. And I'm going to call U right here, at least initially, like I said, for the sake of this argument right here, it's just strictly a function of x. It's just one dimensional. Okay. So our energy here, which is a constant, looks like 1/2 mv squared plus u of x. All right. Now what I'd like to do is to move u of x to the other side and solve for v. All right. So we'll do this in intermediate steps. 1/2 mv squared is equal to e minus u of x. And then I'm going to multiply both sides by 2 and divide both sides by m. V squared looks like 2 over m times e minus u of x. And now I'm going to take the square root of both sides. So when I do that, I get this, right? But velocity, though, velocity is your change in position with respect to time. And this right here is how you get from energy to equations of motion. Okay? So what I'm going to do is to move the t to the left-hand side by itself, or the dt rather, and then move this right over here to the right-hand side, which will put it in the denominator. So on the left-hand side, I'm going to have dt. On the right-hand side, I'm going to have dx over the square root of 2 over m times e minus u of x. Oops. Okay. Now, if I integrate both sides, on the left-hand side, I'm going to go from 0 to t. On the right-hand side, I'm going to go from x naught to x. I get this right here. All right. Now, here's the deal. When you integrate the left-hand side, you're going to get t. When you integrate this side right here, you're going to get something that is a function of position. And you can solve for position as a function of time. The example that I want to use is that of a spring. Okay. So we have sort of our ubiquitous standard spring sliding back and forth on a frictionless platform. I'm going to make some assumptions here. The first thing I'm going to assume is that it starts off from rest. So my initial velocity here is 0. It's been pulled a distance of x naught to the right. Okay. And I'm going to release it from rest. So what we're given is the following. Oh, and it has a spring constant at k. So we're given a spring constant, we're given a mass, we're given that the initial velocity is 0, which really doesn't matter for us right now. And, we're given an initial position of x naught. Now, what I'd like to find is position as a function of time. So basically, I'm finding one of the equations of motion. The next one would be v. You want to find v, you just take the derivative of it with respect to time. Okay. Now, we know, though, for a spring, that our potential energy looks like 1/2 k times x squared. Okay, so this is something that we know. We derived that last time. Okay. So as you can see, you just whip it out. You just pull it right out because we already derived it. We're okay. If we're dealing with gravity, we know what it looks like. So that's the convenience, again, of energy. So watch this. So if you think about the fact that this thing starts from rest, and I look at my initial energy, which incidentally would be the same as my final energy, this right here, okay, then I'm going to have a combination of kinetic energy and potential energy, but it's not moving. It starts off from rest, which means my total energy is strictly potential, which, given the fact that this thing has just been displaced this far from equilibrium, would be 1/2 k times x naught squared. So this is what E is E naught, rather, this is what E naught or E is equal to. This is your total energy right here. That would go into this right here. U of x, though, is just the generic form of your potential energy. 1 half k times x squared. And this x right here can change. In fact, it's this ultimately that we're going to be looking for. Okay? So, that said, let's plug this in. Okay? So, we've already solved for the left-hand side. That's t. On the right-hand side, we're starting off at x naught, and we're ending up at position x, which is what we're trying to find. We have dx here. And sitting under here, we have 2 over m times E. Now, E, remember, is a constant. We've already found out what it is. It's this. It's your total energy. Your initial energy is equal to your final energy because this is energy conservation. E is going to be 1 half k times x naught squared minus the potential energy. The potential energy has this form right here, 1 half kx squared. Okay, this is what we need to integrate. Now check this out. Before we do anything, let's try to clean this up a little bit. So the first thing that we have here is there's a 1 half in front of this term and a 1 half in front of this term. If we pull these over here, the 1 half and the 2 are going to cancel each other out. So this right here is canceled out with these two guys right here. Now the next thing I'd like to point out is that these terms both have k. So I can pull the k out and it would be on the top. So our first simplification makes this integral look like the following. K over m, both of which are constants, times x naught squared minus x squared. Now that's looking a lot nicer. Okay, that's looking a lot cleaner. Okay, now, so next up, I'm going to take this k over m and pull it out. Okay, I want to pull it out in front. You know, just like derivatives, we know that if you have a constant times, an integrand, which is, what this is basically, we can pull the constant out in front and not have to deal with it. When we do, because this is technically 1 over the square root of k over m, what it does is to flip it and cause it to become, in the front, square root of m over k. Whoops. That defeated the whole purpose of that, right? The whole point was to pull that in front. There you go, like that. Okay, so here's our integrand. This is what we're going to integrate. X naught squared minus x squared raised to the 1 half power. So I'm getting rid of the square root stuff here and doing this. Okay, so what we're going to do here is to do a change of variable. All right. What I would like to do is to call x naught times sine of theta. Okay. Now, so what does this do to our limits of integration? Well, at the bottom, x would equal to x naught. So at the bottom, is that. So sine of theta would equal to 1, and theta would equal to the arcsine of 1. And let's see, when is sine of theta equal to 1? Well, the easiest one would be when it's pi over 2. Okay, so our lower limit of integration is going to look like that. Our upper limit of integration is going to be when x is equal to x. You take the arcsine of both sides, and theta is going to equal to this right here. Okay, so why are we looking for theta? Well, remember, part of making a change of variable here is to take the differential. So every time I see a dx, what's the derivative of sine? The derivative of sine is cosine. That's what I want to put there. Okay. So you might look at this and say, oh my God, this looks complicated. Oh no, and then run around weeping and wailing, which, is entirely understandable response to mathematics. But it's not going to be that bad. Now I'm going to call this down here at the bottom theta naught, and this right here is theta. My integral now looks like dx is this. And in the denominator, I have x naught squared minus x squared. Well, this is x. X squared is going to be x naught squared sine squared of theta. And I have to raise that to the 1/2 power because I'm square rooting it, remember? Now check this out. This has an x naught squared. This has an x naught squared. I can pull them out. And when I do, I have to take the square root of them. And when you take the square root of x naught squared, you get x naught. And there's an x naught on the top, which means this is going to cancel out with this right here. And it's going to cancel out with this, making this a 1. Okay. So already we can see that our change of variable has helped us. Now you might be looking at this and going, oh no, what do I do? Well, watch. Sine squared of theta plus cosine squared of theta is equal to 1, right? That's your standard relationship between your trig functions, which means that cosine squared of theta is equal to 1 minus sine squared of theta. And what is this? 1 minus sine squared of theta. So this right here is just cosine squared of theta. And when you take the square root of it, you get cosine. And on the top, you have a cosine. This is going to cancel out with that, which means that the thing that you're integrating at the end of the day looks like this. That's it. That's so easy, right? So we've been doing this one practically all semester. When you do the integration, you get theta, you evaluate it from, final to initial. This becomes theta minus theta naught. So t is equal to the square root of m over k times theta minus theta naught. And we found theta here, and we found theta naught here. Okay, so let's go ahead and plug those in. Now, our goal, remember, was to find position as a function of time. That's this right here. We want to solve for that. So we need to do some cleaning up here. Okay. The first thing I'm going to do is to multiply both sides by the square root of k over m. I'm also going to switch things to the other side. So sine, or the arc sine rather, of x over x naught minus pi over 2 is going to equal to the square root of k over m times t. Okay. Now I'm going to move the pi over 2 to the right-hand side. So square root of k over m times t plus pi over 2. Now, I'm going to take this time, or this opportunity rather, to call omega the square root of k over m. This is done from experience. Typically, though, you don't want to write all this stuff around like that. It just becomes monotonous, and you increases the chances of you making mistakes. So this is the same thing as omega times t plus pi over 2. Now, the presence of omega here is going to make a lot more sense when we talk about rotational motion. Let's just say that it's related to frequency. It's also related to how long it would take for the spring to do one complete oscillation. We're going to see that here in a second. Okay, so the arc sine of x over x naught is equal to omega times t plus pi over 2. Now I'm going to take the sine of both sides. When I take it, I get x over x naught on the left-hand side. On the right-hand side, I have sine of omega t plus pi over 2. I'm going to move the x naught over to the right-hand side. X is equal to x naught sine of omega t plus pi over 2. Next up, I'm going to use an angular relationship that's an identity that looks like this. If you have two angles, we'll call them alpha and beta that are being added together in a sine. This is the same thing. Is sine of alpha cosine of beta plus sine of beta cosine of alpha. Now here, I'm going to call alpha omega times t and beta pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. Which means that I can write this sine omega t plus pi over 2 simply as cosine of omega times t. So our position as a function of time for a spring is x naught times cosine of omega times t. Now, if you remember our conversation last time, springs are an example of a simple harmonic oscillator. They were actually used originally as the first clocks. Okay, so the amount of time it takes for a spring to go through one complete cycle, okay, is analogous to the amount of time it would take for something experiencing uniform circular motion to go through one complete rotation. Omega, if you remember from a long time ago, was also known as angular velocity. How many radians you sweep out over time. And if something is harmonic, that is, it exhibits this periodic behavior, it goes through cycles consistently, this many cycles every second, okay? That's the same thing as saying is that it sweeps out 2 pi radians for every period being the time it takes for one complete cycle. So knowing what omega is here, omega being the square root of k over m, t, the period, would equal to 2 pi over omega, or 2 pi times the square root of m over k. And this ends up being how long it takes for a spring to go through one complete oscillation. And it comes from all this. Okay. Now that said, this right here, this is the correct equation of motion for a spring. Okay. And we got it from looking at energy and solving it. Okay. Now you can get the same solution. You can get the same solution here by solving a differential equation. It's easier, it's much faster, but it also requires a much higher level of mathematics. Okay. And the thing is that this pretty much always works if you can take and you can invoke conservation of energy. All right. Now, so that said, now what I'd like to do is to talk about what happens when you plot energy, because it turns out that if you take and you plot energy, you can actually learn a few things. You can get a sense of how things behave. Okay. And so what I wanted to show you here, and this is just plotting energy. This particular example right here, and let me get my sheet here that's got the numbers on it. hiding somewhere. Not there, not there, not there. Oh, so much stuff here. Then I put it over here. Yeah, here we go. Okay, so in this particular situation, what I did was to just create a plot um, with a rock that has a, this is the falling rock. And in this case, our potential energy looks like mg times h being the height above the ground. And the h here, our height, is 150 meters. And the mass of the rock that we're looking at here is 5.25 kilograms. Okay, so the straight line here would be if you took and you plotted energy against height. This right here is the total energy. So it would be, the same thing, since this thing we're assuming starts from rest. Excuse me. This would be the same thing as m times g times h, where h is 150 meters. Now, so the dotted line that you see here, this blue one, this is kinetic energy. Oh, it's kinetic energy rather. And this line right here, this is potential energy. So the way to think about it is that as this thing falls, it moves this way. It moves from a height of 150 meters to 0. So as it falls, your kinetic energy starts off at 0, but your potential energy starts off at a maximum. Okay. Now, as it falls, you have an exchange through work of potential energy going into kinetic energy. And as you can see, the kinetic energy gets bigger and bigger and bigger and bigger and bigger and bigger. And when it hits the ground, your potential energy has gone to 0, and your kinetic energy has gone to its maximum being whatever the total energy is. Okay. So the nice thing about this is that if you know what the total energy is and you plot that, that gives you limits of motion. Okay. Now I'm going to show you an example of that here with respect to a spring in a second. That said, you can also immediately see that there is a point right here where the kinetic energy and the potential energy are the same. And that point ends up being somewhere around, maybe 75 meters approximately. Okay. And this is all just from taking a look at a plot. All right. So in this next example, what we have is a spring. And in this situation, excuse me, the spring constant is 250 newtons per meter. Our mass is 1.25 kilograms. Our initial displacement, we're pulling the spring and letting it go from rest and letting it zing back and forth, is 0.75 meters. And, like I said, an initial velocity is 0. So this is a spring. Much like this one right here that we had looked at the equation of motion for. Now, so one of the things that you can see here is that when you plot the energy, which, again is in orange, you have a parabola. Okay. Likewise, right here, this is the max energy. Now, just like before, if you release this thing from rest, the initial energy is going to be 1/2 m, or m, 1/2 k x naught squared. Okay. So that's what this is right here. And this is going to be the overall energy in the system. So as this thing bounces back and forth, you can see as you release the spring here, which is this right here is the 0.75 meter mark, there's a transference of potential energy to kinetic energy. This thing is faster and faster and faster and faster. up to right here, which is, the equilibrium position, where the force is zero, so there's, no potential energy there, and all the energy is gone, into making the spring move. So there's your kinetic energy right there. But as you can see here, you can take a look at where the potential energy crosses the total energy. And what that does is to give you a sense of the maximum range of motion of the thing in question. So this thing right here won't move past the 0.75 mark. Just like in the previous example, if you take a look here where the potential energy crosses, the maximum energy mark, you get, 150 meters. So this is a pretty consistent thing. Now, one of the other reasons why, if you remember last lecture, I'd mentioned, springs are a big deal. One of the reasons why they're a big deal is because if you, sort of delve back to your understanding of derivatives and stuff, from calculus, you know that, the first and the second derivative of something, will tell you about curvature and, zeros. For example, if you take the derivative of a function with respect, we'll say, to position, and you set it at 0 and you solve for x, the locations of x tell you about minima and maxima. Right? So for example, if you look at the spring problem here and you just look at the potential energy, 0 is the minimum. That's the minimum of potential energy. And that also happens to be the place where, the force is equal to 0, which makes sense. But the thing is that, no matter how complicated your potential energy might look like, for example, um, you know, uh, actually, let me get rid of y's and x's there, and let's just look at E, we'll say, in x. Okay, so maybe you have a complicated potential energy that looks like this, where it has a maxima there, maybe it slopes down, and then there's a minimum, and then it goes up, maybe something like that. If you were to zoom in, like for example, at this place right here, very closely, and look at this minimum right here, which would be a local minimum, not a global minimum, you would see that it looks like this. Okay, you would see that it has the shape of a parabola. All right. Now, what that means is that for many mathematical functions, or many, we'll say, potential energies, if you look at the minima that they have, and you think of a particle that sits at that minimum point right there, okay, if you were to just give it a little bit of a disturbance, a little bit of, we call it a perturbation, it would oscillate back and forth right here, just like a spring. Okay, so it turns out, and I'm not going to do it, but it turns out that you can take, a potential energy, and you can use a Taylor series to express it. We know a Taylor series look like this. I guess technically this is probably a Maclaurin series, but from 0 to infinity of, we'll say du, dx evaluated, about whatever your point of stability is and whatever your minimum is, times, x minus x naught to the nth power. And this is an inderivative. Actually, it should be there. It should be right here. Derivative of u with respect to x to the nth power. So, n equals 0 would be simply u evaluated at x naught. N is equal to 1 would be the first derivative, and then you'd evaluate that at x naught. And x naught, for example, in this situation would be, this minimum. And if you were to actually perform this expansion, you end up, like for example, if you look at the second term would look like x squared, like this. Okay. So frequently, if you look at small oscillations, around, an equilibrium position, you can model it like a spring, and you can treat that little small area as though it conserves energy, even though the force overall, the potential energy, might not. Okay. So that said, that's one of the reasons why the spring problem is such a big deal, and that's also one of the reasons why plotting energies and stuff like this can be very useful. Like for example, let's pretend that the mathematical function for your potential energy looks something like this. Now let me add another sheet here. Let me just make something up using some circles here. I'll make some minima and some maxima. Let's see here. Use this. Whoops. Put it back over here. Rather use this. Like that. And we'll maybe attach them like this. You'll see what's going on here in a second. So, maybe your curve looks, like this. We'll pretend that isn't there. So, again, here's energy. This would be maybe your potential energy is a function of x. This is x. And, so if you had your problem that you were working and you plotted, the total energy, and the total energy was, we'll say here, like maybe here's the total energy. Whoop. We'll go. So there's your total energy. Then what that means is that if you think of your particle right here, it's sort of constrained to roll back and forth in this potential energy well right here. It'll never make it past here. It won't make it up here. So plotting this gives you a sense of motion as well, because in a situation like this, you could say very easily just by observation that your particle is going to oscillate between these 2 points in space back and forth just like a spring. All right. So this concludes our discussion with respect to chapter 8, and I will see you in chapter 9 for a big discussion about momentum. See you then.